All right, our next adventure, chi-squared, a non-parametric adventure. So you should notice here, spent some time adapting the knight to represent chi-squared. It may not look like it's a fair fight, but this dragon is actually more fierce than he looks. He's got this fire-breathing thing going on. You might see this flame here. It looks a little limp, but it picks up once it gets going. Okay, so intro to chi-squared. First of all, we need to remember some levels of measurements. So if you go way, way back in the day, the distant galaxy far, far away, you might remember nominal, ordinal, interval, and ratio. These are the levels of measurement that we can observe something with. So depending on which level of measurement you're at, you have different options. What we've been working with most of the semester over here is things like R, T, and F. These are parametric statistics. Today we're going to learn about this nominal ordinal tool called chi-squared, which you do with a different kind of data. So what does parametric mean? Parametric is to be understood in terms of a parameter. You're trying to estimate a parameter with parametric statistics. So R, for example, is trying to estimate rho. When you're dealing with non-parametric statistics, that's not the case. So there's not a distribution in the population you're trying to represent with chi-squared. It doesn't work that way. So we have two options here. Excuse me, we have the goodness of fit test, which is roughly analogous to a one-way ANOVA, and then the test for independence, which is analogous to a two-way ANOVA. In both cases, you're using nominal level data. That is like data that just goes in the categories like gender, political affiliation, religion, etc. And you have some observations that you hold in your hand, some sample data, and you want to compare that to some expected frequencies and see if there's a difference there. That's what's going on with the goodness of fit. So we'll work through an example of that now. So let's imagine this is our problem. We want to know if the pattern of political affiliation in South Carolina, that's not Sports Center, in South Carolina is different from the national pattern. So let's imagine nationally we have 50% Democrats, 30% Republicans, and 20% independent. You might say, come on, independents, can't you make up their mind? But no, in fact, they can't. So we just got to leave them there. So what you observe in your sample in South Carolina is 22 Democrats, 22 Republicans, and 12 independents. And you're asking, is this a different pattern of political affiliation than we see nationally? So what are these lines for over here? This first line, this is your observed frequencies. And then down here, this is your expected percents. So here's a workspace you can work this through on, and we'll go step by step. I'd encourage you to go ahead and fill this one out, and then I'll give you the full one later, but take notes as we go. Okay, so 22 Democrats, 22 Republicans, 12 independents. Those are our observed frequencies. And then we have these hypothesized percents, the 50%, 30%, 20%. And we need to then calculate the expected frequencies in terms of numbers, not percents. Well, the way we do that is we say, all right, we got 56 observations total. If we were to get 50% of our sample to show up in this cell, what percent of 56 would be there? What number would, let me say that again, sorry. 50% of 56 would give us what number? So what we do is we take 50%, multiply it by 56, and then we get 28. Cha-boom, we put that in there. And then we're going to calculate these other two cells. So you should figure out that 30% of 56 is 16.8, 20% of 56 is 11.2. Now what? Now we get to use the actual formula. Take a moment and enjoy the graphics. It took me a while to do this. Note the nice chi-squared here replicated for you. Again, fire-breathing dragon. We have now the expected frequencies against the observed frequencies, and we can use our formula. This formula is the summation of each cell. So we got 3 cells, so we're going to have 3 quotients. This is called a quotient, where you got something divided by something. So I take 22 minus 28, square that, and divide by 28. So the first number goes there, the second number goes in the last spot and on the bottom. So take a second, see if you can figure out what the two other quotients would be. Time's up! You should get 22 minus 16.8 divided by 16.8, etc. So now, do you feel the excitement building? You need to resolve each of these, simplify, and then if you add these up, ta-da! You get your chi-squared value, the obtained value. So, to put this in the hypothesis testing context, we take that obtained value, treasure it, and then figure out the degrees of freedom, which is 3 minus 1, or 2, go to the chi-squared table, boom, boom, get the chi-squared critical, ta-ta, compare the two, and we say, drat! We didn't make it, right? Chi-square obtained does not beat chi-squirtical. Chi-squirtical. Sorry, let me try that again. Chi-squared critical. In other words, the pattern of 50% Democrats, 30% Republicans, and 20% independents is plausible. It's plausible that the South Carolina pattern isn't different than the national pattern. I should mention here, there's one limitation when you're doing a chi-squared. You need to have at least 5 expected observations in each cell. So if I would have worked it out where an EF, an expected frequencies, worked out to less than 5, I'd have to stop. It would actually be illegal to continue, and you could get arrested for that sort of thing. Okay, let's do a second example. Let's imagine that you're comparing high school AP classes for all of South Carolina and comparing it to a certain dreamy high school named Lakewood. We're not sure if that's a lake in the woods or a lake next to the woods, but both a lake and a wood are involved. You're going to have the statewide breakdown in high school AP demographics. 50% are white, 40% of the kids are Latino, Latina, and 10% are African American. At Lakewood, because you're near water, you have 21% white students, 14% Latino, Latina, and then 48 African American students. So it would appear that this pattern is different, right? We have more African Americans. So let's see if the chi-squared validates that. A little workspace for you to enjoy. You can fill in this as we go along. So what we should get is that we take 50% times 83, 41.52, 40% times 83, Shazam, 10% to the Shazam. And now we're ready to use the chi-squared formula. So you should get 21 minus 41.5 squared divided by 41.5 here. See if you can get these other two on your own. Go ahead and pause it for a second. Welcome back. You should have gotten as follows. And then if you reduce each of those terms, you should get each of these quotients to 10 point something, 11 point something, 189 point something. Do you see that? This is a big number because this difference is really big. So you get chi-squared obtained of 211, an obscenely large chi-squared. It trounces all over that pathetic little chi-squared critical value, so you can reject the null. And what you're saying is the pattern of ethnic distribution and AP classes at Lakewood are different than those at compared to statewide. All right, that's it for the goodness of fit, and then we will, next lecture we'll tackle the test for independence, the second kind of chi-squared that we're going to learn. I hope you enjoyed.